Hi everybody, my name is Adon Rivas, and I'll be walking you through my art generation project. And for this project, I decided to look at artistic style transfer, and it's a particular application of convolutional neural nets, so that's what the CNN is. And before I continue with the presentation, I just want to go over the notebook that I created, which documents the implementation that of this algorithm that I'm about to present, and it goes through different components of the algorithm and the pipeline. And so I have links to blog posts that I found useful. So if you're curious to learn more, I'm definitely offline, check them out. And then there's also a link to the original source code that I had followed along and mostly modified. So feel free to take a look at it. For my 2 minute presentation, I do go over this. However, for 2 minutes, I didn't do it justice. So definitely check it out on your own time. And there are references to some of the works in literature that have been done on this topic. So jumping back to the presentation, uh, what inspired me to do this was actually this blog post that I came across for this one website that pretty much looks at is focuses on analytics and data science and the NBA. And so while I was in the technical post, pretty much what was just being shared were uh, photos of, game footage of NBA players, and they were remixed by various famous paintings. And I thought this was really cool, one to look at. But when I found out that, uh, you know, deep learning was behind this, I was even more curious uh, to learn more about it. And so that's why I decided to do this as my project. And so what's going on here is that we pretty much have a simple but elegant formula where we take one content image and a style image and combine the two, um, and taking their feature sets independently, so content for one and style in the other, and infusing them to generate a new image, which allows for to create pretty neat art, to be honest. And the first research group to tackle this problem was Gaitis et al. They published the paper in 2015, and they demonstrated that style transfer can, one, be posed as an optimization problem, but two, that it's pretty well suited for convolutional neural networks. And it was definitely a very popular paper that came out in the deep learning community and even the art community. Uh, and it, as you can imagine, inspired several follow-up works. And they get Gaitis et al. They recognize that CNN are really good at feature extraction of images. More so, they can extract features related to content and style. And because there's a lot of work that's been done with CNNs, they mostly deal with problems in computer vision. There was no need to build a new model architecture from scratch. So what they did was they took a pre-trained CNN, utilized the backpropagation mechanics to minimize the objective function that they defined. And so for that objective function, they were looking to minimize the difference in style between images S and G while minimizing the difference in content between C and G. So they defined two loss functions, one for content, another for style, combined the two, and wanted to minimize them both, uh, each iteration that the uh, that the algorithm would run. And you'll see that there are two scalar values, alpha and beta, that help us control which one we want to emphasize more, or if we want to emphasize them equally. And so, just to take a step back and keeping it high level, what's going on here is, so I mentioned that CNNs are good at good feature extractors, and more so, they can extract content features separately from style features. So we do that, get the features that we want given the image, and then with those feature sets, we merge them together to synthesize a new image and arrive at a new piece of art. And pretty much that's all it's doing. Of course, it's a little more complicated than that, and I'll go a little bit deeper uh, in the upcoming slides. But more or less, that's pretty much what's going on. And so for that content extractor, I keep mentioning that CNNs that are being used here, specifically a family of super image classifiers known as VGG nets, were was pretty much implemented. And so this is the pretty much the what's at the heart of the paper. And so these VGG nets were trained on an image data set, excuse me, the ImageNet data set, which is a public repository of images. And if I'm not mistaken, there's an annual competition where, research groups will submit different models trying to tackle different problems in computer vision, and it's pretty much centered around this data set. And so the VGG nets came out of this a couple of years ago, and that just said all they used the most powerful one, or at least the one with the most layers, the VGG 19. And there was a paper that followed up that was released in 2016 that used a simpler architecture of only 16 layers, and that's the one that I used in my implementation. And so what this content extractor is doing is just taking the hidden distance of the raw outputs of C, the content image, and the generate image at various hidden layers. Um, and so pixel by pixel, it's looking at the difference in values. It's square in those, and then summing it for all pixels in for each pixel in the image matrices. And so taking a look at the VGG nets. There are multiple configurations in various steps going from 11 layers to 19. So the one in column E was what was originally used, and then the Johnson et al. Group used the one highlighted in D. And so these VGG nets are specifically used to tackle problems in computer vision. So as you can imagine, they have a softmax layer that outputs different class probabilities for a given image. It's pretty relevant for this problem. So we basically truncate those those fully connected layers at the end in that softmax layer, and just stick with the intermediary layers. And so for style extraction, we're replicating the work of the content extractor, but with one more step. And we compare so instead of comparing the raw outputs, we're comparing the gram matrices of the style and generated images. And to calculate the gram matrix, we just take one matrix and multiply it by its transpose. And why I don't understand it fully, what I do know is that the gram matrix contains non-localized information about the image's style. And so this includes things like texture, weights, and shapes. And so very similarly to what was being done for the content extractor, at each intermediary layer of the network, we would compare the gram matrices between the two images and use that as our loss function. And so we put the two loss functions together and to arrive at our total loss, and then we scale them by alpha and beta. And that's pretty much it. That's all that there is to it. Of course, you can learn a little bit more about the mathematics from what's been by referring to the literature. But to quickly go over some of the results that I did, I have this, I believe what's his Snapchat by DJ Khaled, as on the left is my content image, and then the style image, which is an artwork by Leonid Afremov. And then I played around with different content and style weights. So at a magnitude of 1 and a ratio of 1 to 1, we see that there's very little infusion of the style image's properties, and there's very little change between the third and 10th iteration. And then varying the weights a little bit, it's a very similar output that's generated. So nothing too exciting that's going on here. The only thing that I would say is just at the end, it looks like there is some distortion of the content image as to be expected, but it pretty much just looks like there's been a color filter that's been placed. And now it's going for a little more stark change. We boost the weight of the style weight to 5, and we see that there's a lot more noise, well, you could say noise in the first iteration. It's just being overwhelmed by pretty much different properties or the color scheme of the style image. And by the third image, we get a little more clarity in the 10th image. there's a little finer resolution. And while, as you can expect, there is some distortion into the the clarity of the content image and the structure and outlining of it, but the at least the color schemes and a little bit of the textures of style image has been infused into it, which is more or less what we'd expect. And then I messed around with a couple more configurations by significantly reducing the content weight, and we see that at this point it's just overwhelmed by the properties of the style image. So depending on what your tastes are, you can play around with this and find a happy medium. I personally like this one, um, but it really depends on what you're looking for. And so what I just walked you through was a an arbitrary style transfer algorithm. And there are some limitations to it because while you can just pass in any content style image that you'd want to mix, it is pretty time intensive. So even running it on GPU would take a handful of minutes, and depending on how many iterations you are, it'll take a bit longer. And so there, as I mentioned, there have been follow-up works that have been trying to improve and make advances on the original algorithm. So one of them was looking at real-time style transfer. So wouldn't it be nice if you could train a single neural network um, to basically take a content image and then remix it for a single style image? And that's exactly what a group of researchers did. So the system consists of a new network architecture known as the image transformation network. And that's what's using to generate the final output. And so, through the first iteration, the image transformation network will generate a new image, and that is passed through the VGG network, which has been the lost network, which is known as the lost network here, but that's what it was in the original implementation to begin with. And so we backpropagate the errors of the loss functions into the parameters of the image transformation network to improve the final output so that it becomes uh, it does a better job of combining the style and content features that we are interested in. So what's nice is that, once the network's trained, you just pass in an image, a content image, and then it should generate a new one in a handful of seconds. Um, so the one limitation for this is that if you want to do this for multiple, let's say 10 style images, you need to train 10 different networks. And so the next step was to look at real-time arbitrary style transfer, and there's definitely been work on that. I don't have a slide covered here, but I do have a paper reference at the end of this presentation, so feel free to check that out. Some of those papers are actually released this year, and there's some pretty clever techniques that are being employed there, and it's really cool that you know that the deep learning community has been taking an interest in this, and there are obviously a lot of neat applications and potential applications of of this algorithm. And I haven't had a lot of experience with it, but some of you may have. There's a mobile app I believe called Prisma that's pretty much doing exactly this, where you can take any personal photo that you have and then sort of generate a new one that's been infused with the style of another image. And so basically what it's doing, it's essentially just doing a real-time style transfer. So now you have a better idea of what's going on here. And I definitely learned a lot and actually was fairly excited to take on this project. So I hope you enjoyed the presentation. Thank you.